So this is our physical chemistry practice test. I do apologise about all the shadows of my camera on this. Couldn't avoid it with the way that my lighting works. So I'll go through the multiple choice questions and then section 2. So question 1 is asking you to consider the reaction, and it's N2O4 transforming into NO2, 2NO2. You're told that the enthalpy change is plus 57.2. which means it is endothermic. They're asking you to calculate if the temperature of the equilibrium is increased, what will happen to the equilibrium constant and what will happen to the concentration of NO2. Well, the forwards reaction is endothermic, which means it helps to decrease the temperature. If we increase temperature, the system will try and decrease temperature, so it will do the endothermic reaction. That means it is going to favour the formation of the products. So no matter what, we are going to increase our NO2. So it's either going to be A or it's going to be C. If we're favouring the products, remember our equilibrium constant, capital K, has our products on top and our reactants underneath. So if we're going to be making more products because we're shifting it to the right, it's going to increase our equilibrium constant, so our answer is A. For question 2, what is the concentration of hydroxide ions in a solution with pH 8.5? Well, pH plus pOH equals 14. So if we know the pH is 8.5 plus our pOH, that must equal 14. So 14 minus 8.5 is 5.5. No. Yes, 5.5. So our pOH is 5.5. And to do our pH calculation, or to our pOH, pH is minus the log of the concentration of hydroxide. Sorry, pOH is minus the log concentration of hydroxide ions. So to work out hydroxide ions from pOH is going to be 10 to the power of minus 5.5. And when we put that in our calculator, 10 to the power of negative 5.5, we get 3.1622 times 10 to the minus 6, which rounds up to 3.2 times 10 to the minus 6, which is answer B. Question C. Which of the following represents the enthalpy of formation of a compound? Well, enthalpy of formation of a compound is the enthalpy change when 1 mole of compound is made from its element in their standard states. So the first two cannot be enthalpy of formation because you're not making 1 mole. In the second two, we are making 1 mole. And we look like we are using elements. For C, magnesium is a solid at standard temperature and pressure. Oxygen is a gas at standard temperature and pressure. So those both make sense. So this one works. Sodium is a solid. Bromine is not a gas, it is a liquid. So the only one that has elements in their standard state and that is making 1 mole of product is C. Question 4. Which of the following would have the lowest entropy at 92 degrees Celsius? Well, we've been given 4 different alcohols, and entropy is related to the state of matter. So if I'm given a specific temperature and I'm given things that I can look up the melting and boiling point of, I'm going to see, because if it's a gas, entropy is massive. If it's a liquid, entropy is sort of intermediate, and if it's a solid, entropy is really low. So organic compounds are found on page 10, and if we look through, methanol has a boiling point of 65, ethanol 78, propan-1-ol 97, and propan-2-ol 83. So this one's going to be a gas. Methanol's a gas, ethanol's a gas, propan-2-ol's a gas, but propan-1-ol is a liquid at 92 degrees. Liquids have the lowest entropy, so the answer to that is 4. So you need to look up page 10 to do that one. The next question, Which of the following is true? So looking at this graph. So this is a graph of free energy versus temperature. A reaction is feasible if delta G is negative. So all this part of the graph, the reaction is feasible. So statement A, the reaction is never feasible. Well, that's not true because it's feasible here. The reaction is always feasible. Well, that's not true because we have some parts where delta G is positive. So that one's not true. The reaction is feasible above 300. Well, all of this line is above 300, so that one's true. Final statement, reaction is feasible below 300. No, because below 300, you're in the positive region, which is not what you want for free energy. So the answer is C. Question 6. Which of the following salts forms an alkaline solution? Alkaline solution means you had a strong, oh, I can't spell strong, alk plus a weak acid. So you can tell if something's got a strong alkali because it's got metal in it. So sodium, lithium, potassium, those are all strong alkalis. Ammonium is weak. Then a weak acid. So weak acids are all the acids found on page 14. Sulfate's from sulfuric acid. Sulfuric acid is not a weak acid. Lithium chloride. Chloride is from hydrochloric acid. That is not a weak acid. Propanoate is from propanoic acid, which is one of the acids on page 14. And because it's on page 14, that means it is a weak acid. So you've got your combination. So the answer to 6 is D. Question 7. In question 7, we've been given a titration where we've followed the pH, and you've been asked which of the indicators is not suitable. So if we look here, you can determine whether an indicator is suitable based on the vertical part of the graph. And this one goes from around say about 2.0 to about 8.0. So if an indicator has a range that works between 2 and 8, it will be suitable. If it is below 2 or if it's above 8, it will not be suitable. So you'll need to look on page 14. So phenolphthalein works at 8.3 to 10. So it is not going to work. Methyl orange, it works between 4.4 and 6.2, so it is suitable. Bromothymol blue, there's a load of bromo ones, but bromothymol blue is 6 to 7.6, so that'll work. Bromocresol purple is 5.2 to 6.8, so that one will work. So the one that's not suitable is your phenolphthalein. Right, section 2, first question asks us, what is the second law of thermodynamics? So for a spontaneous process, the total entropy of a reaction and its surroundings must increase. So it means that the reaction can decrease as long as the surroundings increase more, or the reaction can, or if the surroundings decrease, it means the reaction must be increasing more. But combined, they must always increase. Calculate the standard enthalpy change. So enthalpy is H, and you just need to look at the equations at the front. So at the front, your equation for enthalpy change is the enthalpy of formation of your products minus your reactants. So delta H is the sum of your products minus the sum of your reactants. You do have to look at the equation because we do have molar ratios, we do have stoichiometry. So in the products, aluminium is an element, so it doesn't have an enthalpy of formation, but carbon dioxide does. So the products are going to be 3, because there's 3 carbon monoxides, multiplied by minus 111. And for our reactants, well, carbon doesn't have an enthalpy of formation. Aluminium, there's only one of, and it is minus 1669. So when we write that out, it's going to be minus 333 plus, because negative negative is 1669. So that gives us plus 1336, and it is enthalpy of formation, so it is kilojoules per mole. Next, standard entropy change. Well, entropy, it's the same equation, except you're just using entropy. The sum of the products minus the sum of the reactants. So for the products, it is our 198 for carbon monoxide times 3, plus our aluminium, 28, times 2. Then we are subtracting our carbon, which is 6, and there's 3 of them, 3 times 6, plus 1 times 51, so just 51. When we put that all together, we get 581. Now the units this time are joules per Kelvin per mole. So the units of delta H and the units of delta S are not the same. One's in kilojoules, one's in joules. That's going to be important for part D. You can, if you want to at this stage, you can write 0.581 kilojoules per Kelvin per mole for your standard entropy if you want to make sure they're in the same units. As long as you've selected appropriate units and changed them, in this case dividing by 1000 to turn it into kilojoules, that's fine. Calculate the temperature at which the reaction becomes feasible. Well, feasibility is about delta G, and delta G equals delta H minus T delta S. When a reaction becomes feasible, remember it must be negative to be feasible, so the point of feasibility is when delta G equals 0. So we can change delta G to 0 equals delta H minus T delta S, or T delta S equals delta H. We've calculated the values here. I'm going to use the one for kilojoules for S, just so my units all agree. So temperature multiplied by 0.581 equals my 1336. So my temperature is going to be 1336 divided by my 0.581, which when I do that, I should end up with 2299 point something Kelvin, which I can round up to 2300 Kelvin. If you miscalculated either part B or part C, or even both of them, but filled them correctly into this delta G and used the equation properly, you would get all 3 marks. It is 1 mark for correctly doing the calculation, 1 mark for filling in the information correctly, and 1 mark for your calculation matching everything. Right, question 2. Question 2 was all about pH, acids and alkalis. So Bronsted-Lowry definition of an acid, that is a proton donor, or you could write the word proton. Which acid is the weakest? Well, you've been given Ka values and you've been given pKa values. pKa, the lower it is, the weaker the acid, and with pKa, the higher it is, the weaker the acid. Remember, pKa is a bit like pH. The lower the number, the stronger the acid. So the higher the number, the weaker the acid. So propanoic acid has the highest pKa and the lowest Ka, so it is the weakest acid. It's asking for the conjugate base of methanoic acid. So if you're not sure, methanoic acid is one of the weak acids, so you can look it up on page 14. Methanoic acid is the top one. You start with the acid. The conjugate base is going to be the thing on the right hand side, which is HCOO minus. So that is just looking it up. Question B here. 0.88 grams of butanoic acid was dissolved in 250 centimeters cubed of water. Calculate the concentration. Well, butanoic acid is C3H7COOH. And if you work out the GFM of that, it is 88. So our number of moles is 0.88 divided by 88. which is 0.01. Our concentration, C equals N over V, so it's going to be 0.01 divided by 250 centimeters cubed in litres, which is 0.25. And when you do that, you get 0.04 mole per litre, which just happens to be the concentration for the next part. It's asking you to calculate the pH of this butanoic acid. So pH equals half pKa minus half log C. So I like to just get rid of the halves. So I'm going to make 2 times the pH equals pKa minus log C, which the pKa of butanoic acid, if we look it up, is 4.83 minus the log of 0.04. So when I do that, the log of 0.04 taken away from that gets me 6.228, but that was 2 times the pH. So then I divide it by 2, which is 3.114, which I can round up to 3.1. Bottom question is 2-marker. Explain why a solution of sodium butanoate is alkaline. Well, sodium butanoate contains your butanoate conjugate base, which is C3H7COO minus. It will react with water and it will be in equilibrium. It is a conjugate base, so it's a proton acceptor. And we're told it's alkaline, so we are expecting to make OH minus ions. So if we take a hydrogen away from this to make hydroxide, we're going to need to add it on here. So we're going to get C3H7COOH. Also with butanoate, you could write it out CH3CH2COO minus. Oh, sorry, CH3CH2CH2COO minus. That's absolutely fine. But that's not enough to get 2 marks. You can say hydroxide ions are now in excess. So solution is alkaline. Question 3. Use the data to write the rate equation. So first thing, rate equals K, and make sure it's a small k, otherwise you immediately lose the mark. Then what we need to do is look at changing the concentration of each reactant and seeing what effect that has on the initial rate. So for our hydrogen peroxide, if we look at experiments 1 and 2, we can see that the only thing changing is the hydrogen peroxide. We double it and we're doubling the rate, so it's going to be first order with respect to H2O2. Iodine, if we look at experiments 1 and 3, we can see we double the concentration of iodide and we double the rate, so it's also first order with respect to I minus. For hydrogen, if we look at experiments 1 and 4, we double the H plus, but the rate doesn't change, so it's 0 order, so we don't change it. So it's just rate equals K, H2O2, I minus. What is meant by the order of reaction? Well, the order of reaction is the number of species, of reactants, of chemicals or molecules in the rate determining step. Remember that rate is determined by the slowest step, which is called the rate determining step. If you instead said the slowest step instead of rate determining step, you would have also got it, but it's the number of molecules involved in the rate determining step. Overall order, well, you just add up all the orders for each reactant. So H2O2 is 1, I minus is 1, hydrogen is 0, so that gives us 2. Calculate the rate constant. So when you're calculating the rate constant and it's asking you for the units, you can pick any experiment. I'm just going to take experiment number 1. So rate equals K H2O2 I minus. Our rate is 2.07 times 10 to the minus 3. K is what we don't know. Hydroxide is H2O2 is 0.3. Iodide is 0.3. So I'm going to rearrange it for K. So K, small k, is going to be equal to 2.07 times 10 to the minus 3 divided by 0.3, and I'm just going to write squared because it's 0.3 multiplied by 0.3. When I put that in to my calculator, I get a value of 0.023, which gets me 1 mark. I need to put units for the second mark. Now remember the rule, look at how many concentrations are involved. 2. 2 concs. Always take 1 away, so we've got 1 conc. Units for concentration are usually mole per litre, but we always flip them, so it's going to be litres per mole. And because it's rates, we always need to put an s to the minus 1. So our units are litres per mole, s to the minus 1. That would get us our second mark. Bottom question is worth 2 marks. It's asking you to calculate the rate given these concentrations, and it tells us pH. Now pH, with that we could calculate H+, using 10 to the power of minus pH. However, hydrogen's not involved in our rate expression, so we don't need to. So in this case, it's just going to be rate equals K multiplied by 0.5 multiplied by 0.2, which is going to be our 0.023, or whatever value you got here, multiplied by 0.01, which gives us 2.3 times 10 to the minus 3, and rate, moles, litre, seconds to the minus 1. Because it tells you there, you don't need to put it. So they gave you information to try and trick you, which you did not need to use. Right, question 4. I'm not really going to write everything you could write down, but I will talk through this answer. So the action of pH indicators and buffers involves the chemistry of acids and bases. Discuss the roles of acids and bases in pH indicators and buffers. So I would break it down into indicators and buffers. So in indicators, remember your indicator is always, an indicator has H+ ions on it. It will interact with water and it can go to your In- and your H3O+. It can do that. And if you were in a situation, if you had your indicator and you were adding hydroxide ions, it would shift and you would make way more of this than you'd make H2O. If you had your N- and you added H+, in acidic conditions you would make way more of this, H3O+, sorry, and you'll still make water. What you need to say is that In- and HIN are different colours. So when you add alkali, you're going to make more of the In- because it's going to take away protons from the H indicator. If you add acidic conditions, you're going to have way more of the HIN version because it's going to add protons onto the In-. They are different colours, but typically you get colour change when concentration of one is 10 times to 100 times greater than the other. And that would be enough for indicators. Buffers is a bit more that you can say, because you can talk about acid buffers, which is a weak acid plus a salt of a weak acid plus strong base. And you can also say that an alkaline buffer or a basic buffer is a weak base plus the salt of a weak base made with a strong acid. Give the definition of a buffer. A buffer is a solution that holds on to or sustains or maintains its pH upon addition of small quantities of acid, alkali, or water. And you could then talk about how it does by picking any example. So I'm just going to use HA plus A minus because that's the part of the salt. And then I've got my H plus. So if I add, and remember those are in equilibrium. If I add H plus, the concentration of this is going to increase. And so system will try to decrease. So what you'll get is more of this reaction, your A minus going to your HA, and it will keep the pH. Keep the pH by H plus concentration constant. If I take away H plus by adding a base, H plus will decrease, so the system will try to increase H plus, and it will do so by more of the HA ions going into A minus plus generating H plus, and it will keep your H plus constant. You don't have to necessarily talk about indicators. If you say enough about buffers, you don't necessarily have to mention buffers if you're able to talk a lot about indicators. You should be able to talk more about buffers, particularly the definition, give an example of what makes up an acid buffer, what makes up a basic buffer, and then have some sort of equation and describe if you add acid, what does it do to keep the H plus constant when it's been increased? What does it do to bring down the, what does it do to increase H plus when you add a base and it decreases? It's hard for me to say exactly what gets 1, 2, or 3 marks for this. This is just the most full answer that is possible. So that has been a go through of the practice test. You will have similar questions, but it will be longer when you do your real test when you come back after the October week.